All right, so before I start, you know, last week and a half ago, I asked the question at the beginning of the lecture if anybody had a birthday, and nobody did. I asked you what was the probability that nobody had a birthday. So if we assume there's 150 people in the room, and someone down here got it right. So I was thinking about it afterwards. I mean, first of all, it was pretty unlikely that no one would have a birthday, and then I've asked that question several times over the last 15 years, and I think I've asked it to about 3,000 students. And as far as I can remember, only one person ever said that they had a birthday. So assuming that that was true, what was the probability? What was the probability that out of 3,000 students, one of them, exactly one of them, had a birthday on that day? Let's assume there are 365 days in every year.
Can we assume that the question was asked on the same day?
Does it matter? So, tell me.
Okay, it's 1 over 300, let's see, 1 over 365 times 364 over 365 to the 2999.
Good, good. So actually, if you think about it, it doesn't actually depend on the day, assuming that they're all independent of each other. And for that, you get a book. Because I happened to bump into the author the other day, and he gave me a copy of the book, and it's signed. So you can have a signed copy of the book. Good. I'm not going to promise one of those every week. I might have one more squirreled away somewhere. So what I'm going to talk about today is why the internet was designed the way it was. Or if you want to take a cynical approach of what were they thinking of when they came up with this particular idea. Clearly, this is putting the cart wonderfully before the horse, because the purpose of this whole class, this whole course over this quarter, is for you to understand how the internet was designed. So now I'm asking you the question of why was it designed the way it was before we've actually told you the way it was designed. But I thought it would be a fun exercise to do, because you actually know intuitively or actually pretty much everything that you need in order to understand what we're going to be talking about today. So for the next 40 minutes, so between now and 5 o'clock, we're going to discuss a paper that you haven't read. And the reason we're going to finish at 5 o'clock is that I'm going to Chicago this evening, and the boarding time at SFO is 5:45. And okay, well, we'll see whether that works. I might be here tomorrow. We'll see whether that works. But then at 5 o'clock, yeah. So Maria is going to come up at 5 o'clock and tell you about lab number 2, and explain what that funny thing is that's sitting next to her on her right. On her left is TY. So there is a beautiful paper that you will read, because you're all going to take CS244 next quarter. And it's called The Design Philosophy of the DARPA Internet Protocols. Because as I think many of you know, much of the initial funding that led to the creation of the internet was from a DARPA project that was orchestrated by somebody by the name of Bob Kahn, who was working later with Vint Cerf when he was an assistant professor here at Stanford, and that the two of them together created TCP/IP later. But a very influential guy, Dave Clark, who is now he's a research scientist at MIT. I'll tell you about him in a moment. He wrote this paper in 1988, and I'd thought about asking you to read it before today. But you've got a lot on your plates right now. I understand that. You've got a lot of videos to watch. And I'm the guy with the black background. And then there's the programming assignments that you have to do. So I didn't want to burden you with this. And when I was thinking about it, I realized, actually, this paper is so clearly written that if you distill the essence of what he's saying, he organized it so well, you actually don't need to read it in advance to get quite a lot out of it. And you're all going to read it for CS244 anyway next quarter, because it's the very first paper that we read in CS244 for all the reasons that I'm using it today. So Dave Clark was the chief protocol architect for the internet starting from 1981. He continues to be a great visionary today. So this paper was written in 1987. So most of you weren't born, and I was 25. And at that time that it was written as a retrospective a view looking backwards on this thing that seemed to be phenomenally successful called the Internet, and was explaining why it was that it was seeming to be very successful. If you get a chance to read one paper related to this class during this quarter, read this one. It will take you, the first time you read it, it'll take you 15 or 20 minutes. It's a very easy read. It's very descriptive. But you can read it again and again and again and gain more from it because he had terrific insight. And he was very involved in the creation of the original protocols and architecture that was used in the Internet. And you know, I must have read it 10 or 15 times. Each time I read it, I learn something more from that time. To put it into context, he was giving a view that was 1 year after Cisco was created. Routers at that time were actually called Cisco boxes. The IETF started that year, and the number of hosts that were reachable was about 10,000. And NSF, the National Science Foundation, had just gone into the game of trying to create a national backbone in order to popularize the public internet as we know it today. That was before the commercial internet. Can you increase the microphone, please? Okay, well, hopefully that will happen magically, because I can't do it. Did that just happen? Yeah. Wow. So the way that he distills it, he distills it down into 8 goals that apparently were actually explicitly written down at the time. Actually, the paper lists 7. I added one on the beginning because it was kind of so important that it was almost implicit. So I'm going to be going through these 8 goals, starting with this overriding goal, which you've probably and hopefully gathered from what you've read and the videos that you've watched so far. This is a quote directly from the paper, that they were trying to create an effective technique for multiplexed utilization of existing interconnected networks. What does this mean? Essentially, the Internet was created as an internet or a network of networks. That much you know. So the question is, why were they doing that? I don't think it's very well described in any of the papers. In fact, when you hear about layering and encapsulation and things like this, it's easy to think that there was something magical about the particular layers that were chosen or the particular layers that were picked. There are 2 that are going to seem very, very redundant or duplicating of effort, and that's layer 2 and layer 3. They both have addressing schemes. They both have packet formats. They both have unique with some caveats, unique endpoints addresses globally. And so there's definitely a replication function. Why did that come about? Was that because there's some that was coming from some correct design? There was an artifact of this particular goal, which was to create a network that was an effective way to utilize existing networks and interconnect them. The interesting thing is that when the internet was initially designed in the 70s and the 80s, there was a whole group of people that were coming together on a regular basis trying to figure out the basic architecture. They decided that there was too much, way too much installed base of networks around the world in order to take the risk of trying to persuade everybody to change their networks to one common network. Had they been able to, they were totally sure that that's what they wanted to do. So their personal goal was to try and persuade everybody to replace all of their networks with a different one. They just realized that was impractical. So it was actually a pragmatic choice of believing that the right way to build a network, the only way to build a network, was to try and interconnect the existing networks rather than persuade everybody to change. And this has really quite profound consequences. Arguably, a lot of the things that we take for granted as layering today, while with hindsight it's kind of obvious, that was an immediate consequence because they decided that they would build a layer that was building upon the networks that sat beneath. They were going to interconnect the layers, interconnect the networks that already existed. So they needed a way to do that. And of course, the idea of decomposition and layering was not new, but it was immediately became a fundamental part of the design. And I put in quotes this word effective because they didn't really know how well it was going to work out. They knew they needed a addressing scheme in order for packets to find the way to the correct destination, hence the IP addressing scheme. They knew they needed payload in which to put stuff. They didn't really know what else they needed at that point. And in fact, the things that we think of as TCP and IP, that separation, they were actually smushed together to start with. The internet in its first instance was actually a reliable mechanism for communication. TCP and IP were put together, and it was only later that they were separated. The next goal was internet communication must continue despite loss of networks or gateways. These two reasons here are the ones that you'd be most likely to read about, I know, in the New York Times or something, right? It's got to survive a nuclear war, and it was interconnecting a bunch of networks. That's how it got the name of the internet. So that's something that we've all seen before. The internet must support multiple types of communication service. You've heard Phil and I talk about this, that it must support not just voice or faxes or any small set. It's any type of communication that someone would want to use it for, so that over time it could subsume things of different bandwidths, of different scales, of very, very different types of communication. The internet architecture must accommodate a variety of networks underneath. That really is a consequence of goal 0. The internet architecture must permit distributed management of its resources. We sort of take it for granted these days that there is distributed management. In other words, that the network is broken down into autonomous systems which are independently managed, that allowed for the organic growth of the internet. This was actually a radical, controversial design decision at the time, because pretty much all networks, particularly government networks before then, were created in a centrally managed manner. And so it was a pretty controversial point. Goal number 5, the internet architecture must be cost effective. So what do you think? Was it cost effective? What's a measure of whether it was cost effective? How much I pay to access it? Yeah, that could be one measure. Are you willing to pay to access it? It would, if it was cost effective, then perhaps that would. Anything else?
How many billionaires live close to here?
That may not be an example of whether it's cost effective, of whether it was allowed, whether it allowed that phenomenon to happen.
How many organizations elected to replace existing communications infrastructure with using the internet?
So one could argue that its existence today at such a scale sort of suggests that it must have been pretty cost effective, because if it wasn't, then it probably wouldn't have existed. It would have been prohibitively expensive to use. No one would have wanted to use it, and we wouldn't have, was it yesterday, the billionth user of Facebook. The internet architecture must permit host attachment with a low level of effort, and the resources used in the internet architecture must be accountable. So the point about this list is, you don't need to remember this list. And by the way, I'll post these slides afterwards. You don't even need to write it down. But they were an ordered list. They were a strictly ordered list. In other words, 0 is more important than 1, blah, 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 down to 7. And they had no other goals. So of all their goals, this was the least important one. That the resources used in the internet architecture must be accountable. So we'll come back to that one a little bit later. So I'm going to go through these in a little bit of detail now, starting with the first one. So this first goal of building an effective multiplexed interconnection of existing networks, it led to, clearly, different networks being connected together by packet switch store and forward routers. Where did that come from? So anyone want to hazard a guess as to why the different networks connected together suddenly led to this? Do you think that the networks that were being connected together were all packet switched? Probably not. I don't know what fraction were and what fraction weren't. Yeah?
Was it due to congestion on certain networks more than others?
No. Anyone else?
Packet switching, like the lowest common denominator, where you have that in the middle, then you can get to anyone else's other connection?
A large fraction of the networks that they were connecting together, I don't know what that fraction was, were packet switched. And of the networks that they were connecting together, they guessed that it would be far easier to persuade everybody to adopt this technology than circuit switching. It wasn't that this was, I had always thought, and in fact I was a bit puzzled when I realized that this is what this paper was saying. I'd always thought that it had been deduced as the right way to do it. There were many people who were arguing at the time. It just so happens that in the gathering together of a group of people who wrote this paper, it was not particularly, who originally designed the internet, it was not actually particularly high on their mind from a perfection or that this is the right way to do it. In some ways, it was a very lucky choice. It was a very lucky choice because they just felt that there was a growing interest in packet switching for good reason, and that it was a more pragmatic. So there's a lot of pragmatism, a lot of pragmatism. The reason that it was store and forward was, well, frankly, it's much easier to build a router that way, and who was going to care that much if you actually store and forward the packets along the path? So why do you think they chose to interconnect existing networks rather than design one from scratch? Well, I said a little bit about this, that it was a pragmatic choice. Can you now try and put yourself in their shoes of that time? And knowing that at the time that this paper was written, there was only 10,000 hosts that were on the internet. And this was several years, this was a decade into the project. So there was probably less than 1,000 at the time that they started. So does anyone want to take an argument that actually they were kind of cowards and that really what they should have done was to have designed a good network from scratch? Anyone like to make that case? This is much more interesting if we have a discussion. I've heard this before, so more interesting for me if you...
I've heard of preempt that case, which is to say that if they'd done that, probably no one would have used it or would have never caught on, right? That was already a whole bunch of competing standards.
Okay.
And the solution is not to make another proof test one.
Anyone want to take the opposite viewpoint? Say, you know, wouldn't the world be a bit different if they had made a different decision?
Yeah, I think that if they had realized that the scale at which the internet would eventually rise to, then I think it would have been wise for them to choose a different decision.
Okay, so let's say that they had that foresight and said, wow, this thing is going to be huge.
Yeah.
Right? And it's going to change our lives, right?
It looks like today.
What do you think they would have done? So now imagine they'd taken that path. What do you think they would have done? So if you got to play God and be in that position at that time, and what do you think that with what you know so far? I understand you're 2 weeks into an introductory networking class, but I'm kind of curious. At the back.
You put a lot more like security barriers in place.
You think that they would put a lot more security in place at that time had they designed it from, perhaps?
They should have.
Yep. Yep.
They would have privatized it, and then the public would have never seen it.
Maybe. Yep.
You'd have more IP addresses to start with.
They wouldn't have needed this damn IPv6 thing. Yeah. Right. Yeah. So it's interesting to think about, and you can probably come up with many, many reasons. I'm not going to dwell on these now. Just think about this during the quarter. Again, that there's sometimes luck is really, really important. And there was a certain amount of luck in picking the interconnection of existing networks, which forced them to create something that was very simple, that essentially had to be open, that wasn't dependent on the physical layer, and it built in this immediate separation of layers and hiding of the dependence on the network below. Okay, I don't want to dwell on that too much, but this minimum assumptions of the interconnected networks that they wanted sitting below led to a sort of few interesting consequences. They wanted to be able to transport a datagram of reasonable size with reasonable chance of delivery. Right? That's what they were trying to do. Right? And then they built in right in to the delivery mechanism this reliable retransmission early on. So there was this interesting comment that's made in this paper. Reliability and qualities of service were not built in because they would require too much change. Datagram was used as a building block, not as a service. In other words, that was originally just a sensible unit to use because it was simple to build the system. Reliability and qualities of service were not built in because they would require too much change. What does that mean? Oh, actually, you haven't. Go ahead.
If you were to, it sounds like kind of what they were trying to do is make their protocol not be, make the features of their protocol not be like too excessively like have it not be like excessively more feature rich than the underlying things that we're connecting. If you had quality of service in the internet protocol, but then you didn't have it in the protocols that you're connecting to, then it's only of limited use because the thing you're interfacing with doesn't have constant quality of service. It's like, okay, well, whatever, not going to happen.
So let's stick with something that we probably all know to start with, what it might mean for the network to be reliable. Right, so reliability can mean several things here. Reliable in terms of the ability to route around a failure, reliability in the ability to retransmit data that is lost, packets that are lost along the way. So it's interesting that the reliability, the idea of different types of service that would be presented to the user, and reliable, and the ability for it to robustly recover from error, were not thought of as important characteristics up front. Now we take that for granted now. Now I want you to put into the perspective of this was designed by the US military for a network that was designed to withstand a nuclear attack. Okay? So we take this so much for granted that you're probably all thinking, what is he talking about? Right? Can you imagine what the generals who were funding this thought when they said, here you are, your job is to take millions of dollars of taxpayers' money and put it into building a network that would withstand nuclear attack, and you're not going to build in reliability? It's not built in as a basic part of the mechanism. I mean, these were true pioneers, right? I mean, they were considered by many as crazy at the time, and they wanted to make it open, and they wanted to standardize and publish everything about how it worked. So things that we take entirely for granted now were extremely, extremely controversial stances to take at the time. And there are some people who think that the only reason that it kept going was that no one took it seriously, and so it was allowed to flourish on its own, because all the generals were thinking, well, this can't possibly succeed. It'll never amount to anything. So the internet communication must continue despite loss of networks or gateways. This was one of their requirements. Entities should be able to continue communicating without having to reestablish or reset high-level state of their conversation. So this leads to a fate-sharing model, which is you only lose communication state if the end host is lost. In other words, there's no communication state maintained in the network. So they took this as a logical consequence of that particular goal. So this idea that there's no state within the network corresponding to a particular connection or a particular communication fell out from this desire to make sure that communication would continue despite loss of networks or gateways. For example, a bomb lands on them, or they fail, or the power fails. So this led to the idea of stateless packet switches, which led to the idea of datagrams. So that kind of just drops out as a building block as a consequence of that. I'm going to jump on from this. So the second goal, I'm just going to go through each of these in turn. The internet must support multiple types of communication service. What does that mean? Does anyone want to say what might these multiple types of communication service be?
So they might be either on top or below it.
Uh-huh.
So below it, you can think of sort of different ways of transmitting packets, like copper wire, fiber, even electric wires, potentially wireless. And then above it, like in terms of communication service, you have voice, you have, I guess, the World Wide Web, different services. So that's how I'm interpreting it.
Yeah, and not only types of application, but the expectations of those applications. How might they differ in terms of what those applications might expect?
Yeah, so some might require more, like more reliability. Some might require constant stream of packets.
Right. So this was another area in which it was considered very controversial. So the design and the original architecture was considered very controversial because the only large-scale global network that existed at that time was the telephone network. And that provided one type of service. That was phone calls. That was even before fax machines. And so the idea that you would build a network that would support multiple types of communication rather than them existing on different networks. At that time, in addition to the telephone network, there was the TV network, there was cable, there was the radio network. And they were all existed to offer a particular type of communication for a particular type of application. So again, something that we take for granted now, this was a very deliberate decision that it must be able to encompass many, many types of communication. And the thing that they explicitly set out to do was to not only support the types of communication that they could think of, was to try and figure out how you could architect a system that would support many types of communication that they couldn't think of, that they hadn't yet thought of. And that's clever. That's very clever. But that they argued very hard that this was essential for the military, that the military would need this because the military would need to carry many different types of traffic. And you can imagine why they would want to carry video and voice and things like that. And so, again, it was considered a fairly radical departure from the way that networks had been designed up until that point. The idea that it would accommodate a variety of networks, as was suggested here, the military obviously had things like packet radio networks and all sorts of different types of networks around the world that they wanted to be able to subsume into this particular design. Yeah?
Where did ISDN stand in its development at the time?
This was a long time before what was called the Integrated Services Digital Network.
Because the phone companies, AT&T, Marvell,
that's right.
to push
Yes.
that direction as well.
That was probably about 15 years after this as an alternative to try and integrate many and support many types of service onto the traditional telephone circuit switched network. So the internet architecture must permit distributed management of its resources. So first of all, I want to ask, what are the assuming that we believe that it accomplishes this, we'll come to that question in a moment, what are the consequences of it? What are the consequences of permitting distributed management of resources? I touched on it earlier, but tell me more.
Well, you'll also, I mean, it's more public, it's more open, there's no one internet king, I guess, that can actually dictate the management of resources. It's distributed, and so it's, I think, much more open, I think.
So a big consequence, yes, go on.
Someone can steal DNS and redirect all traffic through China for
Yeah.
a couple hours.
Uh-huh.
Means that since there's no centralized management, you have to be ready for backwards compatibility back to the beginning.
Why is that?
Well, if there's no centralized management of resources, if you want to push an update to something, you don't have control. Whoever decides things doesn't have control over what software or hardware everyone is running.
Okay.
So it has to be completely backwards compatible.
Some other consequences?
Tons of political consequences, which
Okay.
makes it interesting that the military located this.
And commercial consequences? What are the commercial consequences of this, do you think?
There's no need to pay to part of it.
You might have to pay to get connectivity. You might have to pay someone to persuade you to connect to them.
If you have your own devices, you don't need to pay to have access to the right to connect to the.
You don't necessarily have to pay someone to manage your portion of the network. You can create your own network and then connect it, and you probably have to pay somebody in order to be able to connect it. But the very reason that somewhere like Stanford can have its own network managed using many of the same mechanisms and then just pay somebody to connect to the outside world, or any company, or you at home, comes really as a direct consequence of this. But there was a more important consequence, which was during the 1990s, when there was this geometric growth in the number of different autonomous systems that were connecting to the network. Because they could all be, the story on the street was that, mom and pop would set up, would establish their own ISP, and then they would connect to others around them, and they would just peer using BGP or whatever there was that they needed to use at that time in order to connect to the rest of the network. They would just manage their piece, and as long as they behaved across the connection to everybody else, then the whole system would organically grow. So it led to this phenomenal organic growth. So this decision, which was based on the idea of limiting the ability of an attacker to bring down the network by having multiple parts that were operating independently. What they had not foreseen was the stupendous commercial growth that would follow from different entities, both commercial and non-commercial, being able to create pieces of the network. I would put this down, if I was keeping track, I would put this down to luck again. right? Because it was designed with a different, I mean, it was with a great vision of, well, systems are more likely to grow, scale, and survive if you have this sort of autonomous control and the sort of distributed management of the resources. I think it's fair to say no one actually imagined what the consequences would be of that design choice in allowing that enormous growth during the 1990s. Well, let me come back to this one. So actually, to what extent does it accomplish it, that goal? Do you have any sense of the degree to which it's distributed in its management, the resources are managed in a distributed fashion? Is it true?
I think one could argue both ways. Because, I mean, DNS and IP, like, even though they're distributed, like, everybody controls their own DNS, there's still a central management service.
So what are some of the central, so DNS to some extent there is a central part of that, right?
And IPs as well.
IP addresses, the naming.
I would disagree with that because you can get a class of an IP address, and then you can use CIDR to route within your organization how you see fit to divide up those subnets.
Sure, but that would also be true. You get some autonomy in how you use them, but where you get them from is coming, I mean, it's hard to think of any other way than them coming from some authority, and then somebody has to decide how that resource gets divided up. And that becomes very controversial and political, and we'll learn about that more in the quarter, some of the politics associated with that. Someone who hasn't said anything yet.
So what about security? You can't do anything about security to distribute that. Basically, there are a few companies in the world that can issue certificates for SSL. And can basically let everybody to issue certificates for.
So while there have been methods that have grown up to provide some element of trust and security in a distributed fashion, it certainly makes the problem harder, right, than if you require up front that everybody connect in a way that's under your control and that you manage the connectivity. So it was setting themselves up in a way for a little bit more difficulty in figuring out how you would make the system secure. Obviously has many elements to it, but many aspects to it, but certainly has a consequence of making it a little harder to secure the system. Yeah?
I have a follow-up to that, which is, how much do they care about security at this point? I mean, it was ostensibly a military research.
So it's interesting. Did you see it on the list?
What?
No. I was going to ask that question later. Okay. Yeah, it's good. It's not on the list. In fact, many of the earlier internet RFCs, as soon as they actually even had a section in that was about security considerations, most of them say none. And it was not generally. So can anyone think of a reason why you would have a network that was originally funded by the military? I mean, some of these design choices are bizarre considering where it came from, and that it doesn't even mention security when it's supposed to be the military network that interconnects all of the establishments in the US.
If no one else was able to connect to it, then there's very little chance of some outside attacker coming in and messing with you.
Well, yes, that might be the case. Had they been thinking that this was not going to actually connect with anyone on the outside, that would have been a fair assumption to say, I will assume that there's an air gap between this network and any other network. It's a bit hard to imagine today, but at that time, that's not actually the reason, but that would have been a reasonable, I think, guess. At the back.
Neither of the other networks that were available were secure at that time.
It was largely not in the air. Yes, that's right. But actually, it was discussed and considered at length. And it was believed at that time, which I think there's a lot of evidence to say that this is true, that for most questions of security, the right way to do is to solve it end-to-end and not actually solve it in the network itself. And so there was an appreciation and understanding that the majority of things that you would like to do with whether it's concealing the content through encryption or authenticating the sender or either end of the communication, that it was better handled end-to-end, even though the particular mechanisms had not been created at that time to do so. That there would be other aspects, for example, the difficulty of identifying a sender or denial of service attack. They weren't really considered at the time. So the internet architecture must be cost-effective. I talked about this earlier, right? So I said, by one definition, it's incredibly cost-effective because there's billions of people using it. So it must have been. If it wasn't, then we wouldn't be using it. So maybe that question is moot now. So, but what decisions do you think that this led to? What were the consequences of making, it wasn't very high up on the list, but it was on the list. What were some of the things that they might have done that you suspect that they didn't do to keep it cost effective? Yeah.
I mean, maybe just add like more complex implementation to, you know, I don't know, maybe just they realized that they would have to make a very minimal design that wouldn't be super expensive for other networks, the existing networks, to implement on top of there.
One of the things that when you learn about the end-to-end principle is that there was a very distinct goal early on with the internet to make the whole of the forwarding infrastructure, the routers and the links, dumb and minimal. And there are words that those two words get used a lot, dumb and minimal. And one could argue that it was because of the end-to-end principle of saying you should put the functionality at the edges, or that's the only place where you could correctly implement it. And therefore, in many cases, you shouldn't try and put it in the middle because there's no point. On the other hand, there is something to be said for that was a description after the fact, that really a lot of that simplicity came from this goal here, which was to keep it cost effective, which was to keep it very, very simple, and so that it would be very easy. The forwarding a packet in dedicated hardware in 1970, even at a few kilobits per second, was challenging. In fact, the boxes that were specially built by a special government contractor in order to be able to forward packets at a few thousand bits per second, something that we would laugh at today. They were racks of equipment the size of me, right? And it was not an easy thing to do, to be able to create something like that at the time. And so keeping it very, very simple so that the cost would be low, so that many people would be able and willing to build and sell them, and so that you'd have a number of, it would be an effective design. What else? So that's in terms of the nodes. What about the links? What else is there about the network that is sort of seems to be cost effective, or someone seems to have been thinking about the cost?
Maybe by using the layering principle, it's easy to switch out the link for another sort of link type if
okay. Yep.
transmission goes fast enough.
Uh-huh. What about the way in which we use the links?
They don't have to be reliable.
They don't have to be reliable, right? So we can use flaky links.
They're shared as much as possible.
They're shared as much, so statistical multiplexing that comes as a consequence of packet switching. So the efficient usage of expensive long-haul links, because those links were extremely expensive. It totally dominated the cost at the time. So being able to use them efficiently by having the statistical sharing. The resources must be accountable. This was a goal of the internet. The resources must be accountable. What does this mean? Yeah. Interesting. It wasn't one that was on my list, but yes, great. I guess it's a resource and it's accountable. Okay. Internet addresses are unique IP addresses. Arguably they're not, but they were at that time. Anything else? You're all thinking, all the ways in which I can think that they might have been, it's clearly the internet wasn't designed that way, so I'm not going to say it. What are all the ways in which they could have made it accountable then that they didn't? What are some of the things that could have been done? Okay, so I should tell you, accountable in this context is to do with accounting, money. Yes, not as in hold someone accountable in this context. Sorry, I should explain that. Yes, at the back.
They could have kept track of how much data is being transmitted by certain.
Right, so sort of usage accounting. And in order for what? What might you use that for? Billing somebody, right? You might use it in order to send them a monthly bill like the telephone company does. Arguments are often made that the telephone system, that the billing mechanism is about as expensive or complex as the telephone system itself. It's hard to separate the two actually in practice, but it's clearly a very large fraction of the overall complexity in order just to be able to collect that bill and send it to you. The internet doesn't do that much. It does a little bit of it, right? There's a little bit of usage-based billing, but it's clearly not built into the infrastructure, and it certainly wasn't at this time. It was a goal. It was a stated goal. It was on the list that it would be accountable, and they would account for these things. So it dropped off the list. It was on the list, and it essentially dropped off the list because they realized that in order to meet the other goals, it was going to make it prohibitively expensive or complicated and unreliable and blah, blah, blah in order to be able to do this, right? So it essentially was not done. This perhaps was one of the most dramatic choices, was to fail to meet this goal. In the sense that they would have done so, it's a useful exercise to go through and say, what if you actually reversed all of these goals and put this one as number one? What would you end up with? You would end up with a system that was very, very different. And would it have taken off and been as successful as, in fact, it has been? Right? And I think I would personally argue that had this been higher up on the list, it would have been a disaster. Right, because the whole thing would have been how you extract money, and people who are trying to extract money tend to keep things closed and build high walls, and then we wouldn't have had the open internet that would have grown so organically. So, whew, lucky choice, right? But why did they choose to make it so, in the end, that it wouldn't be accountable, in the sense that you wouldn't be able to charge people, just because it was difficult, and also because in a military network you didn't really have to? Luck. I put it in that category of immense amount of luck, right? That decision turned out to be fine for them to make. Okay, so I was going to ask what's such a. So originally TCP and IP were joined, but they were later split. So why were they split? Should all be able to stand up and announce this loudly.
To allow for the unreliable protocol.
I'm sorry?
To allow for the unreliable.
That would be one way, to allow for the choice of having an unreliable transport service on top of IP, or to be able to, in a sense, facilitate UDP. That would be one way of thinking about it. What would be another reason for separating them?
Too many devices on the network. You needed to be able to do NAT, stuff like that.
They were separated out from a layering perspective, not from an, I mean, yes, okay, it meant that the code was separated. It's not as though TCP was placed in the routers. We're talking about the implementation of that functionality at the end host.
Certain things would work much slower if they needed the TCP reliability. So certain things really need everything that TCP offers, and therefore they just have like UDP and like build on.
So it enabled UDP. Yeah, I think we've covered that one. Any other? Why do we have layering again? Should all be able to say this. We have layering because it gives us this decomposition and allows for not only for a UDP, but future versions of TCP, because you can then potentially come in and exchange it. You've got a well-defined API on the top and the bottom, right? So it's a and allows for a additional beyond TCP and UDP, and there are a bunch of others that that you'll see later in the quarter that operate at the same layer.
So you might want to have a different addressing scheme other than just IP. For example, going to IP6.
Right. So it then allows for both parts to change independently. Right. It's so long as the service is well defined. So here's the author's conclusion. So if you've only got 1 minute and you don't have 15 minutes to read the whole thing, just read the conclusion. The last time I read this, which was a couple of years ago, I nearly fell off my chair. He basically said, right, and I called on this recently. So you know this choice of a datagram? Yeah, that's what he said in the paper. Yeah, maybe it wasn't such a good thing after all. That's what he was saying in 1987. It was good for most of the goals, but it was kind of poor for the rest of them. And there was probably a better way we could have done it. Processing packets in isolation, it makes the resource management and the accountability all rather too hard, because a packet is part of a communication. And if you've got some representation of the communication itself in the network, then it's easier to do these things. So he was anticipating some soft state in the network and this is not just him, they were anticipating at the time that this idea of datagrams would come to be replaced with something that was different later. Okay, and it hasn't, and I don't think it will. So, but if you think of, yeah, I'm going to stop in a moment. If you think about the there's a sort of a subtle point here, and I just think about this during the quarter when you think of some of the other functionality that is placed into the network. When you start to learn about what a network address translation device does, or a firewall, or any kind of security device, there are many devices that sit in the network whose function it is to try and figure out the communication that this packet belongs to in order to do their job. They might be load balancing a flow, they might be inspecting inside the data to figure out, and so they try and reassemble the communication to which this belonged. And so essentially they're trying to reestablish the flow of communication in order to figure out what to do. So you'll see this tension in which some of these things could clearly have been built more easily had there been a concept of some soft state in the, or some state in the network indicating that there was a flow. So there is a price to pay, and I think this is the conclusion to take, that we often take granted that things are strictly better than, A is strictly better than B in every sense, and that it is an engineering trade-off that was made, and there are consequences. I don't want you to come away from the end of this quarter thinking that there is somehow something divine about the design of the internet. There were some choices that were made. They were extremely smart choices, but then in most cases there is a trade-off associated with it. If we can help you over the period of this 10 weeks to get to the point where you not only understand that yes, those design choices were extremely good and smart and almost certainly the right ones, but that they come with some consequences, then we've done our job. With that, I'm going to stop and hand it over to Maria, and I'm going to run to the airport. So I see.